Welcome to Pump Design Lab. This is part one of our Boundary Layers series. We will begin with the most basic question. Why does fluid slow down when it touches a wall? Once that idea is clear, everything else in the series, friction, turbulence, separation, and pump losses, will have a logical foundation. The question nobody asks. When we draw flow through a pump, we often show clean arrows moving smoothly through the impeller and volute. But real fluid does not move at one uniform speed everywhere. The important question is this: what happens to the fluid immediately next to a solid wall? The answer is the starting point of the whole topic. Near a wall, fluid slows down dramatically. To answer that question, let's leave pumps for a moment and use an example everyone can picture: air flowing past a moving car. Wind outside a moving car. Imagine placing your hand outside a moving car window, far from the car body. The air moves at almost the same speed as the vehicle, but right at the painted metal surface, the air is not rushing past at that speed. The air in direct contact with the car's surface is essentially stationary relative to the car. Between the stationary air at the wall and the fast air outside, the velocity must rise gradually. What we have just observed has a precise engineering name. It is called the no-slip condition. The no-slip condition. This fact is called the no-slip condition. Fluid touching a stationary wall has zero velocity relative to that wall. It applies to water, oil, air, and almost every real engineering fluid we deal with. If the wall itself moves, like the rotating surface of an impeller, the fluid immediately touching that wall moves with the wall. Viscosity is the reason the wall can grip and slow the nearby fluid. But saying that fluid sticks to the wall only gives us the result. Next, let's understand the physical reason behind it. Why does fluid slow near a wall? Think of a pack of cards. If you hold the bottom card still and push the top card sideways, the cards in between move at different speeds. Fluid behaves similarly. The wall slows the fluid touching it. That slow layer drags on the layer above it. Then, that layer affects the next layer. Viscosity transfers this slowing effect from the wall outward into the moving fluid. This viscous interaction gives us two very different velocities: zero at the wall and full flow speed farther away. So the next question is obvious. How are those two velocities connected? Two velocities that must be connected. So we now have two conditions that must be connected. At the wall, the fluid velocity is zero, far away from the wall. The fluid moves at the main flow velocity, often called the free stream velocity. The change cannot happen suddenly, like a step. Instead, the fluid passes through every velocity between zero and the outer flow velocity. The region that bridges those two velocities is a boundary layer. Definition of a boundary layer. The boundary layer is a thin region near a solid surface where viscosity has a strong influence on the flow. Inside this region, velocity rises from zero at the wall to almost a free stream velocity outside it. It is not a separate type of fluid, and it is not an added layer of material. It is simply the part of the flowing fluid that has been slowed by the wall. Once you know what a boundary layer is, you begin to see it everywhere that fluid touches a surface. The boundary layer exists everywhere. Boundary layers exist wherever fluid touches a wall. They form over aircraft wings, inside pipes, around valves, inside elbows, and on every wetted surface of a pump. In a centrifugal pump, they form on the pressure side and suction side of each blade, on the hub and shroud, through the diffuser, and along the volute walls. This is why boundary layer knowledge is essential in hydraulic design. And that brings us back to pumps, where the number of wetted surfaces is large, and the passages are much more complex than a simple flat wall. Why pumps cannot ignore it. Ideal fluid theory is useful because it gives us a clean starting point. But ideal flow has no viscosity and no wall friction. A real pump has many curved walls and narrow passages. So boundary layers are unavoidable. They consume energy through friction, distort the velocity field, promote secondary flow, and can separate. Much of the difference between ideal oiler head and actual pump performance begins with these real near-wall effects. Before moving ahead, let's pause and lock in the central idea from this first section. Why does fluid stick? The main point so far is simple. A wall slows the fluid touching it. Viscosity spreads that slowing effect into the fluid above the wall. The zone where the velocity changes from zero to the outer flow value is the boundary layer. It may look thin, but it is where many of the most important hydraulic losses begin. Now that we know what a boundary layer is, we can ask a second important question. Does it stay the same thickness, or does it change as flow continues along a surface? Start with a flat plate. To understand how a boundary layer grows, start with the simplest possible case: water flowing over a long, smooth, flat plate. The plate is stationary, and the incoming water is moving from left to right at a uniform speed. This model is simple, but the same physical process later appears on curved pump blades and casing walls. We will answer that using the simplest possible model: water flowing over a flat plate. What happens at the leading edge? At the leading edge, the water first meets the plate. The fluid particles touching the plate must immediately slow to zero because of the no-slip condition. Just above them, the water is still close to the incoming velocity. Therefore, right at the leading edge, the region affected by the wall is extremely thin, almost zero in thickness. At the leading edge, the effect is almost invisible, but the story changes as the fluid travels farther along the plate, moving downstream. Now follow the water farther along the plate. The water has spent more time traveling beside the wall. The slow layer next to the wall has had more time to drag on the fluid above it. As a result, the region influenced by wall friction becomes thicker. The boundary layer grows continuously as we move downstream. A simple way to remember this growth is to think about how long the fluid has been exposed to wall friction. The fluid has known the wall longer. A useful way to remember this is to say that fluid farther downstream has known the wall longer. Near the front edge, the wall has only just started slowing the fluid. Farther along the surface, viscosity has acted for a longer time. That longer exposure allows the wall's influence to reach farther into the main flow. This means that boundary layer growth is not an unusual event. It is a normal feature of every real flow over a surface. Boundary layer growth is not optional. Whenever a real fluid flows along a surface, a boundary layer forms and grows. The exact growth rate depends on fluid viscosity, flow velocity, surface roughness, and pressure conditions. We cannot eliminate this behavior in a practical pump. The engineering task is to understand it, reduce the losses it creates, and prevent it from separating where possible. However, the wall does not influence the entire flow equally. We need to distinguish the outer flow from the near wall region. Outside the boundary layer. Outside the boundary layer, the flow is much less affected by viscosity. Its velocity is close to the free stream value, and ideal flow equations can often describe it reasonably well. This explains why Bernoulli-style analysis can be useful in the outer flow. But it is important to remember that this ideal picture fails close to a wall, where friction and shear are dominant. Outside the boundary layer, ideal flow thinking can often help us. But inside the layer, viscosity becomes a dominant player. Inside the boundary layer. Inside the boundary layer, velocity changes rapidly with distance from the wall. This velocity difference between adjacent layers creates shear. Shear produces friction, and friction converts useful mechanical energy into heat. In pump passages, the boundary layer is therefore not only a geometric detail, it is a real source of hydraulic loss. Boundary layer thickness. We usually represent boundary layer thickness by the symbol delta. There is no perfectly sharp edge where the boundary layer suddenly ends. So engineers use a practical definition. The boundary layer edge is often taken at the location where the velocity reaches 99% of the free stream velocity. Beyond that point, the wall's influence is small enough to neglect from many calculations. To discuss the layer properly, engineers need a practical way to define its thickness. Flat plate to pump passage. A flat plate is only the first picture. Pump passages are much more complicated. They are curved, rotating, expanding, narrowing, and turning the fluid. Still, the basic principle does not change. Every wall produces a slow near-wall region, and every passage gives that region time to grow. In pumps, several boundary layers can interact with each other at the same time. The The flat plate has helped us see the basic idea. Now, let's bring that picture closer to the curved and rotating passages inside a pump. How the boundary layer grows. From this, we can conclude that boundary layers begin extremely thin when fluid first meets a surface. They grow as the fluid moves downstream. Outside the layer, the flow may behave almost like ideal flow. Inside it, viscosity, shear, and energy loss are important. This simple flat plate picture will now help us understand the velocity profile. We now have the first foundation. A boundary layer starts at a wall and grows as fluid travels along that wall. In the next episode, we will look inside this layer and understand the velocity profile, the smooth ramp from zero velocity to the main flow speed. That is the end of Part 1, why boundary layers exist. In Part 2, we will explore the velocity profile inside the boundary layer and then introduce its two personalities, laminar and turbulent flow. If this explanation helped you see real fluid flow more clearly, subscribe to Pump Design Lab. Our goal is to build pump hydraulics from first principles, one concept at a time. Welcome back to Pump Design Lab. In Part 1, we learned that a wall slows nearby fluid and creates a boundary layer that grows downstream. Now we will look inside that layer. The key question is, how exactly does velocity change between the stationary wall and the fast outer flow? What is a velocity profile? A velocity profile is a picture of how fluid speed changes from the wall outward. Imagine a graph. One axis represents distance away from the wall, and the other represents fluid velocity. At the wall, velocity begins at zero. As we move outward, the velocity increases until it reaches the free stream value. Every velocity profile begins at one non-negotiable condition, the fluid velocity at the wall. Velocity at the wall. The most important point on every boundary layer profile is the wall itself. At a stationary wall, the velocity is zero. This is the direct expression of the no-slip condition. It does not matter whether the outer flow is slow or extremely fast. The first layer at the wall is held back by the surface. From that stationary wall condition, the velocity gradually recovers as we move outward. Velocity away from the wall. As we move away from the wall, fluid is less directly affected by wall friction. Its velocity rises gradually. Eventually, it becomes almost equal to the main flow velocity. The boundary layer is the entire region over which this gradual recovery from zero to full speed takes place. This gradual recovery is worth emphasizing because it is easy to imagine it incorrectly. A ramp, not a cliff. It is important not to imagine a sudden jump from stationary fluid to fast-moving fluid. Real fluid gives us a smooth ramp, not a vertical cliff. Viscosity continuously transfers momentum between neighboring layers. That is why the velocity curve changes smoothly from a wall out to the free stream. The shape of this ramp is not only visual. Its slope has a direct physical meaning: shear stress. Velocity gradient. The steepness of this velocity ramp is called the velocity gradient. Near the wall, the gradient can be very large because velocity rises from zero over a small distance. This gradient matters because wall shear stress is related to it. A larger velocity gradient generally means a larger friction force between the wall and the fluid. Let's now translate that velocity gradient into the actual friction force acting on a wall. What is wall shear stress? Wall shear stress is the friction force per unit area acting between the fluid and the wall. The wall pulls backward on the fluid, opposing its motion. The fluid applies an equal and opposite friction force to the wall. In a pump, this shear stress exists over all wetted surfaces, and the total effect contributes to hydraulic loss. But friction alone is not the entire story. The shape of the velocity profile also tells us how strong or weak the near wall flow is. Why profile shape matters. The profile shape tells us whether the fluid close to the wall still has enough forward momentum. A full, healthy profile has relatively strong forward motion near the wall. A weak profile has a large zone of very slow fluid close to the surface. That weak near-wall fluid is the first part of flow to fail when it meets a rising pressure. We can describe that weakness more precisely as a momentum deficit. Boundary layer as a momentum deficit. Compared with ideal flow, the boundary layer carries less momentum because friction has slowed it down. You can think of this as a momentum deficit near the wall. The outer flow may still be moving strongly, but the low-energy region close to the wall has less ability to resist a difficult pressure rise. This is a hidden weakness inside every boundary layer. This is exactly where the idea becomes important for centrifugal pumps. The first pump connection. Inside an impeller passage, velocity profiles develop on the blade surfaces and on the hub and shroud walls. These layers occupy part of the flow passage and reduce the region carrying high-energy flow. They also make the exit flow non-uniform. This affects the real outlet velocity triangle, the hydraulic losses, and ultimately the head and efficiency of the pump. Velocity profile is a ramp, not a cliff. Before continuing, let's summarize what the profile has taught us. The boundary layer is a smooth velocity ramp from zero at the wall to the outer flow velocity. Its steepness creates wall shear stress. Its slow region represents a momentum deficit, and its shape tells us whether the near wall flow is healthy or approaching separation. So far, we have described a boundary layer as though it always behaves smoothly. In reality, it has two very different possible personalities, laminar and turbulent. Two personalities of a boundary layer. Boundary layers do not always behave in the same way. They can be laminar or turbulent. A laminar boundary layer is smooth and orderly. A turbulent boundary layer contains chaotic mixing and small eddies. These two states have very different friction losses and very different abilities to stay attached to the surface. Let's begin with the more orderly state, the laminar boundary layer. Laminar boundary layer. In a laminar boundary layer, fluid moves in smooth layers that slide past each other in an organized way. There is little mixing between layers. A particle close to the wall tends to remain close to the wall, while a particle farther out tends to remain farther out. The motion is quiet, predictable, and orderly. Because this motion is orderly, it has one important benefit: relatively low friction. Why laminar flow has low friction? Because laminar flow has little mixing, often produces lower skin friction drag than turbulent flow. Imagine traffic where every car remains in its lane, moves smoothly, and makes no sudden changes. The result is orderly motion with relatively little disturbance. Laminar flow can therefore be desirable when surface friction reduction is the main objective, but low friction does not mean that laminar flow is always the best possible condition. The limitation of laminar flow. But laminar flow has a weakness. The slow fluid close to the wall is not constantly replenished with high momentum fluid from outside the boundary layer. When pressure starts rising downstream, this near wall fluid can lose its forward motion quickly. So laminar flow often separates earlier than turbulent flow in an adverse pressure gradient. As flow continues and disturbances grow, a laminar boundary layer can change into something much more mixed. Transition from laminar to turbulent. As the boundary layer grows, the smooth laminar pattern may become unstable. Small disturbances from roughness, vibration, upstream turbulence, or high velocity can grow instead of dying out. The flow then changes through a transition region and becomes turbulent. Reynolds number helps us judge whether inertia is strong enough compared with viscosity to encourage this change. That new state is the turbulent boundary layer. Turbulent boundary layer. A turbulent boundary layer contains many small, irregular swirling motions called eddies. Fluid mixes strongly across the layer. Fast fluid from the outer region is carried toward the wall, and slow fluid from near the wall is carried outward. The motion is more chaotic, but it also changes the momentum distribution in an important way. This strong mixing improves one aspect of the flow, but it also comes with a cost. Why turbulent flow has more friction? This strong mixing transfers more momentum toward the wall. As a result, turbulent boundary layers usually have higher wall shear stress and higher skin friction loss than laminar layers. Turbulence is therefore costly if friction drag is the only concern. But in many real machines, separation is a much larger loss than the added friction. The surprising benefit of turbulence is that it gives the near wall fluid more energy and momentum. Turbulence has a superpower. The major advantage of turbulence is that it brings high momentum fluid down close to the wall. This re-energizes the near wall region. The turbulent velocity profile is called fuller because more of the layer moves at a velocity closer to the free stream value. That fuller profile can keep moving forward even when pressure rises downstream. This creates one of the most important trade-offs in fluid mechanics. The engineering trade-off. This creates a classic engineering trade-off. Laminar flow gives lower friction but may separate easily. Turbulent flow gives higher friction, but resists separation more strongly. The correct design choice depends on the situation. If early separation would create a large wake, a stall, or a major diffuser loss, a turbulent boundary layer may actually provide the better overall performance. In the next episode, that trade-off becomes critical. We will see why a low-momentum boundary layer can detach from a surface, creating separation, the source of some of the largest losses in pumps and diffusers. Laminar and turbulent boundary layers. From this, we can be able to understand that laminar boundary layers are smooth, orderly, and relatively low drag. Turbulent boundary layers are mixed, higher drag, and fuller near the wall. The important lesson is that turbulence is not automatically bad. Its mixing can give the boundary layer the momentum it needs to remain attached. That is the end of Part 2, Velocity Profiles, Laminar Flow, and Turbulence. Next, we will explain boundary layer separation using simple analogies, aircraft wings, diffusers, and surprising lesson of a golf ball. Subscribe to Pump Design Lab for practical, step-by-step explanations of pump hydraulics and rotating fluid machinery. Welcome back to Pump Design Lab. In Part 2, we learned that boundary layers contain slow, low-momentum fluid near a wall. Now we will see the consequence when that weak fluid meets a rising pressure. This event is called separation, and it is one of the most important causes of real hydraulic loss. Separation, the boundary layer failure. Now we come to the most important consequence of boundary layer behavior, separation. Separation occurs when the low-momentum fluid next to the wall can no longer continue forward along the surface. It slows down, stops, and may reverse direction. The main flow then lifts away from the wall, leaving a recirculating and highly wasteful region behind. To build the intuition, let's compare the boundary layer with something familiar, a cyclist trying to climb a hill. The bicycle hill analogy. Imagine riding a bicycle downhill into a valley and then climbing a hill on the other side without pedaling. Going downhill, you gain speed easily. Going uphill, you lose speed. If the hill is too steep or too long, you eventually stop and roll backward. Boundary layer fluid faces the same problem when it must move into a region of rising pressure. In fluid flow, that uphill or downhill effect is created not by elevation, but by pressure change. Favorable pressure gradient. When pressure decreases in the direction of flow, the fluid accelerates. This is called a favorable pressure gradient. It is favorable because the pressure field helps move the fluid forward. Even the slow fluid near the wall receive assistance. Boundary layers under favorable pressure gradients tend to remain thin, attached, and stable. Adverse pressure gradient. The opposite situation is where the real challenge begins. Pressure rising in the direction of flow. Adverse pressure gradient. When pressure increases in the direction of flow, the fluid must decelerate as it moves forward. This is called an adverse pressure gradient. The near wall fluid, already slowed by friction, must push against this rise in pressure. It is like a tired cyclist trying to climb uphill with very little speed left. The outer flow and the near wall flow face the same pressure rise, but they do not have the same ability to overcome it. Why the near wall fluid fails first? The outer flow has higher velocity and more momentum, so it can often pass through a moderate adverse pressure gradient. But the fluid next to the wall has already lost much of its momentum to friction. It is the weak part of the flow. When the pressure rise becomes too strong, this near wall fluid stops first. When the low momentum near wall fluid finally loses that struggle, separation begins. The moment of separation. At the separation point, the forward motion very close to the wall falls to zero. Wall shear stress also falls to zero at this point. Farther downstream, the near wall flow may reverse direction. The flow that was following the wall contour can no longer stay attached, and a recirculating pocket forms between the wall and the main flow. And once separation occurs, it is not a small local detail. It changes the entire flow field downstream. What separation creates? Separated flow is expensive. It creates recirculation, turbulence, and a large loss of useful energy. It can reduce pressure recovery, distort the downstream velocity distribution, and make flow unsteady. In pumps, this unsteadiness may appear as hydraulic noise, pressure pulsation, vibration, and a reduction in head and efficiency. Aircraft wings provide the most familiar large-scale example of this process. Aircraft wing stall. A familiar example is an aircraft wing stall. At a normal angle of attack, air remains attached over the wing surface and produces lift efficiently. At too high an angle, the pressure rise over the rear part of the upper surface becomes too severe. The boundary layer separates early, lift drops sharply, and drag rises. A stall is fundamentally a separation problem. The same physics appears in internal passages as well, especially in diffusers. Diffuser separation. A diffuser creates the same challenge in internal flow. Its area increases, so continuity tells us velocity decreases. As velocity decreases, pressure rises. That pressure rise is the purpose of the diffuser, but it is also an adverse pressure gradient. If the diffuser opens too quickly, the boundary layer cannot stay attached and pressure recovery collapses. Before entering the pump, let's look at one final everyday example that explains why controlled turbulence can sometimes be useful. The golf ball lesson. The golf ball gives a beautiful example of controlled turbulence. A smooth ball often develops laminar flow that separates early, creating a large wake and high-pressure drag. Dimples trigger turbulence earlier. That turbulent boundary layer has more near-wall momentum and stays attached farther around the ball. The wake becomes smaller, and the ball travels farther despite slightly higher skin friction. Now we can bring the full story into the centrifugal pump, where boundary layers are present on almost every hydraulic surface. Boundary layers in a real pump. Now bring these ideas into a centrifugal pump. Boundary layers form on every wetted wall. The pressure and suction sides of impeller blades, the hub, the shroud, diffuser vanes, the volute, and discharge passages. Pump hydraulic performance depends not only on the main flow path, but also on how these wall layers grow and interact. Let's first identify the two most important blade surfaces: the pressure side and suction side. Each impeller blade has a pressure side and a suction side. The pressure side generally experiences higher static pressure. The suction side generally has lower pressure and higher local velocity. The pressure distribution around these surfaces is what turns and accelerates the fluid, but also determines where the boundary layer is likely to remain attached or separate. Of these two surfaces, the suction side is often especially sensitive to boundary layer separation. Suction side boundary layer. On the suction side, fluid commonly accelerates near the leading edge and reaches a high velocity. Farther along the blade, it often needs to decelerate before leaving at the designed exit condition. That deceleration means pressure rises downstream. Therefore, the suction side boundary layer often faces an adverse pressure gradient and becomes a critical separation location. The severity of this risk depends strongly on how aggressively the blade is loaded. Aggressive blade loading. If blade loading is too aggressive, the pressure change is demanded too quickly. Excessive curvature, rapid blade angle change, or high inlet incidence can make the suction side pressure recovery too severe. The boundary layer may then separate before reaching the trailing edge. The blade no longer guides the fluid in the way the designer intended. If separation occurs, it does not merely create local loss. It changes the energy transfer that the impeller was designed to produce. What separation does to pump head. Euler's equation assumes a particular change in the fluid's tangential velocity, but when separation occurs, the flow does not follow the blade cleanly. The actual exit flow angle changes, the whirl component may be lower than expected, and the real head falls below the ideal theoretical head. Separation is therefore directly connected to the gap between theoretical and actual pump performance. And we must remember that blades are not the only walls inside an impeller passage. Hub and shroud boundary layers. It is not enough to think only about blade surfaces. The hub and shroud are also walls, so they develop boundary layers from impeller inlet to outlet. These layers can become thick and interact with the blade-to-blade pressure field. The resulting flow is fully three-dimensional, not the simple two-dimensional picture used in basic velocity triangle analysis. These hub and shroud boundary layers interact with the blade passage pressure field and create a three-dimensional effect called secondary flow. Secondary flow. Pressure differences across the blade passage and the curvature of the passage can drive low-momentum boundary layer fluid sideways. This cross-passage motion is called secondary flow. It can carry slow fluid from the hub or shroud toward one side of the passage, often concentrating low-energy fluid in corners where separation is more likely. That secondary flow tends to transport low-energy fluid toward particular vulnerable regions, where low-energy fluid collects. In many impeller passages, low-momentum fluid can accumulate near the shroud and close to the suction side toward the outlet. This is a vulnerable region because the flow has already traveled through the passage, boundary layers have grown, and pressure recovery may be occurring. Local stall and recirculation here can strongly distort the impeller discharge flow. The diffuser and volute then face their own separation challenge as they attempt to recover pressure. Volute and diffuser boundary layers. The diffuser and volute are designed to convert some kinetic energy into static pressure. But because they expand the flow passage, they naturally create adverse pressure gradients. A well-designed diffuser recovers pressure gradually while keeping flow attached. A poorly designed diffuser can separate, producing non-uniform flow, recirculation, lower pressure recovery, and increased hydraulic loss. Finally, boundary layer behavior can connect directly to one of the most damaging pump phenomena, cavitation. That is the end of Part 3, separation and its effect on pumps. In the final part, we will study boundary layer control, the practical design methods used to reduce separation, improve pressure recovery, and protect pump efficiency. Subscribe to Pump Design Lab and continue building your understanding of real pump flow, not only ideal equations. Welcome to the final part of our Boundary Layers series on Pump Design Lab. We now understand why boundary layers form, how they become laminar or turbulent, and how they can separate. The final question is practical. What can a designer do to control this behavior and reduce the losses it creates? What is boundary layer control? Boundary layer control means deliberately managing the near wall flow so that it remains efficient and attached. The aims are to reduce friction losses, delay separation, improve pressure recovery, and reduce unsteadiness. Some methods are passive and come from geometry. Others are active and use added energy, suction, or injective flow. Although many control techniques exist, they all follow two simple strategies. Two ways to prevent separation. Nearly every boundary layer control method can be understood using two simple rules. First, give the weak near-wall fluid more momentum. Second, reduce the adverse pressure gradient that the near-wall fluid must overcome. Some methods do one of these. Some do both. This is the central logic behind the entire control toolkit. The first and most powerful strategy is to prevent an excessive pressure rise from appearing in the first place. Control Method 1. Shape the pressure gradient. The cleanest and most powerful method starts during design. Do not create an unnecessarily severe pressure rise. Use smooth curvature, gradual area changes, and well-distributed blade loading. If the flow is turned and decelerated over a longer distance, the boundary layer has a much better chance of remaining attached. Diffuser design gives us a very clear example of how geometry controls the pressure gradient. Diffuser angle control. Diffuser design is a classic example. A diffuser must increase pressure, but it should not do so too suddenly. A longer diffuser with a gentler divergence angle normally gives the boundary layer more chance to survive. If the included angle is too large, separation becomes likely. Practical simple diffusers often use conservative included angles, commonly in the approximate range of 8 to 12 degrees, depending on application and inlet conditions. The same philosophy applies inside the impeller, where blade curvature and loading determine the pressure recovery along the passage. Blade curvature and loading control. The same discipline applies to impeller blades. Avoid sudden changes in blade angle and avoid concentrating too much turning near one small part of the blade. Spread the velocity and pressure change smoothly along the camber line. Smooth loading reduces the severity of suction-side adverse pressure gradients and makes separation less likely. When geometry alone cannot prevent separation, engineers may sometimes use a second strategy, deliberately energizing the boundary layer. Control Method 2. Trigger turbulence deliberately. Sometimes a designer deliberately promotes turbulence to avoid a larger separation loss. This is the golf ball idea. A turbulent boundary layer creates more skin friction, but it also has more momentum near the wall. If that extra momentum delays separation significantly, the total loss can be lower than with a smoother but weaker laminar boundary layer. One passive way to do this is with vortex generators. Vortex generators. Vortex generators are small tabs or vanes placed on a surface. They create controlled streamwise vortices. These vortices pull high-momentum outer fluid down toward the wall and lift slow near-wall fluid outward. In this way, they re-energize the boundary layer and can delay separation. They are common in aerospace and may be used in selected turbomachinery applications. A more direct but more complex technique is boundary layer suction. Boundary layer suction. Boundary layer suction removes the slowest fluid next to the wall through slots or porous surfaces. By extracting this low-momentum fluid, the remaining boundary layer becomes thinner and relatively stronger. It can resist a more severe adverse pressure gradient. Suction can be highly effective, but it requires hardware, ducting, and power, so it is not common in ordinary centrifugal pumps. The opposite approach is to add momentum directly through boundary layer blowing. Boundary layer blowing. Boundary layer blowing does the opposite. Instead of removing slow fluid, it injects a thin jet of high-momentum fluid along the surface. This directly boosts the near-wall flow and can delay or even reattach separation. It is like giving our tired cyclist a push uphill. Again, the method needs energy and added complexity, so it is usually limited to specialized designs. There are also practical geometric and surface-based tools that influence near-wall flow. Splitter vanes, surface finish, and riblets. Splitter vanes are a practical geometric method for wide diffuser passages. By dividing one wide passage into narrower passages, they reduce the effective diffusion demand and help control separation. Surface finish also matters. Smoother surfaces generally reduce friction. In specialized applications, tiny streamwise grooves called riblets can modify near-wall turbulent structures and slightly reduce turbulent skin friction. At this stage, the important realization is that boundary layers are not isolated effects. They are present across the complete hydraulic passage of every pump. Boundary layers are everywhere in pump design. At this point, we can see that boundary layer science is not a separate topic sitting outside pump design. It is present in every hydraulic passage. Every wall creates a slow layer. Every bend, expansion, and pressure recovery process tests that slow layer. The quality of pump hydraulic design depends greatly on how well these layers are managed. Let's now connect all the physics through one simple cause and effect chain. The chain of events. The chain is straightforward. Wall friction creates slow near-wall fluid. That fluid contains less momentum than the outer flow. If the passage creates a strong adverse pressure gradient, the slow fluid loses forward motion. Separation follows. Then recirculation, pressure loss, non-uniform velocity, noise, vibration, and lower efficiency can appear. This chain explains why real pump design is more demanding than simply calculating theoretical Euler head. The core pump design challenge. A pump is not simply a device that adds energy to liquid. It must add energy while guiding the liquid through rotating, curved passages without creating excessive loss. Euler's equation gives the theoretical energy transfer. But the difference between theoretical and actual pump performance is shaped by friction, boundary layers, secondary flow, mixing, leakage, and separation. One of the clearest examples of design stage boundary layer control is smooth blade loading. Why smooth blade loading matters. Smooth blade loading is not merely an aesthetic preference in CAD. It controls how pressure changes along the blade. When the pressure recovery is spread smoothly, the boundary layer can remain attached. When the blade asks the flow to turn or decelerate too abruptly, the low-momentum near-wall fluid is more likely to separate. Good blade design is boundary layer control built into the geometry. The same discipline is essential in the diffuser, where the desired pressure recovery can be lost if expansion is too aggressive. Why conservative diffuser design matters? A diffuser is supposed to recover pressure, but pressure recovery only works if the flow remains attached. An overly short or steep diffuser may look compact and may promise strong theoretical recovery, but separated flow can destroy that benefit. In many cases, a gentler diffuser with lower ideal recovery can deliver better real recovery because the boundary layer remains attached. Even a good hydraulic design can experience stronger losses when the pump moves away from its intended operating point. Why off-design operation matters. At the best efficiency point, flow enters and leaves the pump passages close to the intended angles. At part load or overload, incidence changes. These changes can increase blade loading, strengthen adverse pressure gradients, and enlarge separated regions. This is one reason efficiency, vibration, and hydraulic stability often deteriorate when a pump operates far away from its best efficiency point. Those off-design losses do not affect efficiency alone. They can also affect vibration and long-term reliability. The link to efficiency, vibration, and reliability. Attached flow supports good pressure recovery and high efficiency. Separated flow wastes energy and creates unsteady recirculation. That unsteadiness can cause pressure pulsations, noise, and vibration. Over time, vibration can add stress to bearings, seals, shafts, and structural components. Boundary layer management, therefore, matters not only for efficiency, but also for pump reliability. We can now reduce the whole topic to one clear sentence. The one-sentence explanation. Here is the one sentence to remember. A boundary layer is a thin region near a solid wall where friction slows the fluid down. It becomes dangerous when this low-momentum fluid cannot overcome a rising pressure and separates from the surface. That separation is one of the most important causes of loss and instability in real hydraulic machinery. And we can reduce the entire control philosophy to two equally clear rules. The two rules of boundary layer control. And here are the two design rules to remember. First, give the near-wall fluid more momentum using methods such as controlled turbulence, vortex generators, suction, or blowing. Second, reduce the pressure rise it must fight using smooth blade loading, gradual diffusion, controlled curvature, and splitter vanes. In most pump designs, the second rule is the most practical and powerful. Let's finish by bringing the lesson back to practical pump design. Final takeaway. Boundary layers may be thin, but they control a major part of real pump performance. They explain why ideal flow calculations are not enough, why diffusers need careful angles, why blade loading must be smooth, why off-design operation creates losses, and why separation can lead to vibration and cavitation risk. Good hydraulic design is, in many ways, the art of keeping flow attached for as long as possible. If this episode helped you see pump flow more clearly, subscribe to Pump Design Lab. In the next topic, we can connect boundary layers directly to hydraulic losses, slip, and the difference between theoretical and actual pump head. You have now completed the boundary layers and boundary layer control series. Remember the main message. Boundary layers are thin regions near walls where friction slows the fluid. If the slow near-wall fluid faces too strong a pressure rise, it separates. Good pump design protects the flow by keeping pressure recovery gradual and by maintaining enough momentum close to the wall. If you found this series useful, subscribe to Pump Design Lab. In the next episode, we can connect boundary layer losses to slip, hydraulic efficiency, and the difference between theoretical and actual pump head.